Okay, so we're going to start off with some review board questions from the stuff we did before, so make sure you try these on your own before I go through them. Okay. So what's important is if I give you a graph, you need to use the graph to find it. Don't use the formulas because they won't always get you the right answer. Okay, use the graph and that'll help, right? So spring constant you need to know is slope, and I'm going to ask you that on your quiz as well, so make sure you know that. So to find the slope, we would just use these 2 points. So it's going to be y2 minus y1 over x2 minus x1. And our points that we're picking are going to be, oops, sorry, there we go, 256 newtons minus, looks like our bottom one is 0 newtons. Okay, and then our x2 is 9.5, but remember to look at the units, right? It's 9.5 centimeters. Centa is times 10 to the negative 2. So instead of saying centimeters, we can say times 10 to the negative 2 meters, right? So it's 9.5 times 10 to the negative 2 meters minus 1.5 times 10 to the negative 2 meters. If you forget that times 10 to the negative 2, you're going to get it wrong, which is annoying because you know how to do it. Okay, so we plug this in, 256 minus 0 divided by 9.5 times 10 to the negative 2 minus 1.5 times 10 to the negative 2. And we get our answer, 3.2 times 10 to the 3. So B is the correct answer. Okay, same graph. Work done is area, right? Spring potential energy or work done is area. So we want to find this area. So it's a triangle, so we have to use base times height divided by 2. So my base goes from 9.5 to 1.5. So this is a base of 8, right? But remember, it's not just 8. It's 8 times 10 to the negative 2 meters. Can't forget that. Okay, and then our height is 256 newtons. It's got to be newtons and meters, and we divide it by 2 because it's a triangle. So if we do that, we go 8 times 10 to the negative 2 times 256, and we divide that by 2. We get 10.24, so it looks like D is the correct answer. Okay. So a spring has an elastic constant of 5.6 times 10 to the 2. If the spring is initially in its equilibrium position, what is the stretch? What is the stretch of the spring caused by a force? So we have a force, right? We have a spring constant, and then it's looking for the stretch, so that's going to be x. So this one's very straightforward. Fs equals kx. So we just need to take our I guess we'd have to move this down here like that to find our stretch. So we take our force, which is 325 newtons, and then our spring constant, 5.6 times 10 to the 2, and we get 0.58 meters. So B is the correct answer. Okay, and the last one, the work required to compress a string a distance of 24 centimeters from its equilibrium position if it has an elastic constant of 5.6 times 10 to the 4. So that's our spring constant, that's our x. Yeah. So we have to use our spring potential energy formula, 1/2 kx squared. So 1/2 times our spring constant, 5.6 times 10 to the 4 newtons per meter, and then 24 centimeters, so 24 times 10 to the negative 2 meters, or 0.24 meters. Either one's fine, so whatever one you want to use. So we plug all that into our calculator. So 1/2 times 5.6 times 10 to the 4 times 24 times 10 to the negative 2 meters equals 6720. B is our correct answer. Okay. So this is our last lesson in the unit. It's a very short unit, law of conservation of energy. That's what we're going to go through today. So, systems. In Science 10, we learned 3 different systems. We learned an isolated system where energy and matter cannot enter or leave. So the example of that is we're boiling this water over this flame, and we have an open top, so the water particles can go out top, and also heat leaves out the side here. So heat is the energy, water is the matter. They can both enter or leave our system. Okay. So an example of that would be, boiling water with the top off, an ice. Oh, sorry, I was reading this wrong. Sorry, I was doing the wrong one. Sorry, I started with isolated system. This is our isolated system. So energy, matter cannot enter or leave. Sorry, zoned out a little bit there. So inside of here, if heat tries to escape, well, this is like a thermos cooler, so it's sort of trapped inside of here, right? And we got our stopper on here, so water can't leave there. So a thermos is a good example of that. A thermos isn't totally isolated, because if you leave something in a thermos over a couple days, eventually that heat will leave. So a thermos isn't perfect, but it's as close as we can come. Okay, a closed system. Energy can enter or leave, but matter cannot. So this is our closed system right here, where water can't escape, but heat can escape off the side there. So because energy can enter or leave, but matter cannot, that's a closed system. So this is, if you boil a pot of water with a lid on, that's an example. Earth is a good example of this, because the sun gives us energy, energy leaves, but not a lot leaves the Earth. It's not totally true, right? People leave the Earth technically, but not considering the mass of the Earth. The mass of the people that leave is not that big. Same with like asteroids coming in. It's not that much. So we can say Earth is relatively a closed system. And then an open system, which I explained at the beginning, is matter and energy can leave. So if we take the cap off, water can escape out the top as steam, and energy can leave off the side. So pot without the lid would be the open system. Humans are an open system, right? Energy can enter, energy can leave. That can leave as heat. We eat food, we poop it out. So matter can enter or leave. So these are examples that we learned in Science 10. Okay, so in physics, it's important that we define our systems based on what part of the problem we're looking at, right? So if I showed you this and I said a ball falls, well, what we could look at is we could look at this as our system. Okay, so whatever you're looking at your system, everything else is the surroundings. So this is the surroundings out here. So because we know that the ball's falling, but what's going to happen is this ball looks like it's going to gain kinetic energy. So as it falls, it's going to gain energy. So that means that work is being done by gravity. And what we're doing is we're changing our kinetic energy. So if we're just looking at the ball is gaining energy. So the ball, so if we were trying to classify this system, this would be a closed system. Because matter, the ball isn't changing size, it's not breaking apart or anything, but that ball is gaining energy, so we would consider this a closed system. But if we looked at this same problem a little bit differently, and we looked at the ball Earth system, so this is our system, and this is our surrounding out here, well, the ball is still gaining kinetic energy, but when we have the Earth, we sort of have context, right? So now we know that the ball has potential energy here, and as it falls, it gains kinetic energy. So energy isn't really being added or removed, it's just being changed. It's changing from potential to kinetic as it falls, right? So this is an isolated system if we look at it like this. And we need to look at things a little bit differently. So if we looked at this first system over here, and we used a physics principle, and we're using this is physics principle number 3. But if we look at this one, well, we can actually use physics principle number 5 to do this one, which we haven't learned yet. It's the law of conservation of energy, where energy is being converted from one form to another, but none of it's being lost. All of that energy is staying within our system. And even if there's friction, it's still going to the air within our system, this box here. So same problem, just two different ways of looking at it. So we need to definitely define what our system is, put a box around it, put a circle around it, before we can say what type of system it is, and both will work. So law of conservation of energy, energy cannot be created nor destroyed, it can only be changed. And in an isolated system, energy is always going to be conserved, right? Energy is always going to stay in this bubble here. So this is a formula. This is really physics principle number 5. And this is the way that we can write it. So this is new. This is a Greek letter called sigma. And what sigma means is sum of. So if I sum up all of my energies before and I sum up all of my energies after, they should equal each other if my system is isolated. None of my energy is being lost. Okay, so physics principle number 5. Here we are. This is what we're using to do this. So a term that comes up is total mechanical energy. And total mechanical energy is just a sum of all the kinetic and potential energy. Don't forget spring, including spring, and should remain constant if our system is frictionless, right? So our mechanical energy is just whatever kinetic and whatever potential, right? And this can include spring potential energy. If there is friction, you're going to lose some energy in the form of heat, right? So if the system has friction, some of the energy will be created in the form of heat. So we can still look at it the same way, but we need to include heat as part of our mechanical energies. We have kinetic, we have potential, and we have heat here. Okay, and we don't really have a symbol for heat. We just write heat out because heat is a form of energy. So here we have a 100-gram coffee cup, and it falls off a 1-meter high table. Assuming no friction, complete the following table of mechanical energy. Okay, so here's the coffee cup up here, and it's on top of a 1-meter tall table. So we can use MGH to calculate how much potential energy it has, right? Because the coffee cup is 100 grams, or 0.1 kilograms. And the table is 1 meter high, and G is 9.81 meters per second squared. And the table is 1 meter tall, right? So if I calculate this, which is pretty easy to calculate in your head, I get 0.981 joules. And because my coffee cup hasn't fallen yet, I don't have any kinetic energy. So if I wanted to find my mechanical energy, I would just add these two together, and I would end up getting 0.981 joules of kinetic energy. Okay. So we can represent this in a bar graph. So here, starting off, we have all potential and we have no kinetic energy. Okay. So bar graphs are a good way to represent this conservation of energy, right? And if we want to look at the thing, we're sort of looking at this as our system. We're not looking at the coffee cup by itself because we want to see how that energy is transformed, right? And all of our energy is staying within this box here. So we are saying that it's an isolated system. And we are ignoring friction, so we don't even have to worry about heat in this one. So the second easiest one is looking at the bottom here. So it looks like it's on the ground, but we'd look at it just before it hits the ground where it's going the fastest. So if all of our energy stays within our system here, our mechanical energy should just stay the same. The total amount of energy is our mechanical energy, so all of these should be 0.981 joules, right? And if it's just about to hit the ground, it's going to have 0 joules of potential energy, so that means, well, this plus whatever this is has to equal 0.981. So I know that my energy is 0.981 joules for kinetic energy. So all of my potential gets transformed into kinetic, and we can show that in our bar graph, right? So at this halfway point here, well, we have to do some calculations because it still has some potential energy here, but it's also moving, so it's going to have kinetic energy. So I can do a calculation. So 0.1 kilograms, and still 9.81 meters per second squared. And now it's half a meter off the ground. Okay, so if I do that calculation and I go 0.1 times 9.81 times 0.5, I get 0.4905 joules, right? And I don't know how fast it's moving here, but if I know that 0.981 is going to equal this plus this, then I just have to go 0.981 minus this, and I get 0.4905 joules, right? Because this plus this is going to equal this. So now half of my energy is in the form of potential, and half of my energy is in the form of kinetic. My total mechanical stay the same. So my total mechanical would be represented by the amount of bar that I have here, right? So you can see that potential is going down, kinetic is going up, and that's how we can solve that question. So solving law of conservation of energy questions, you want to state the law of conservation of energy before doing the question. You want to list the different types of energy involved before and after, and then you just have to solve the question. They're not that tough. Okay, so now this is a different style of question. So same coffee cup. Calculate the maximum speed of the coffee cup just before it hits the floor from the 1 meter tall table. Okay, so what I want to do is I want to write out that law of conservation of energy. So my energy before equals my energy after. And I don't want to write out before and after all the time, so I just use a little tick to represent after. Okay, so if I draw out my coffee cup, so here's my coffee cup here, and here's my coffee cup here. So this is my before and this is after. Before we said it just had potential energy, and then after it just has kinetic energy. So my energy before, if I sum them all up, well, it's only one of them. It's just potential. And then after, well, it's just got kinetic energy. So EP is equal to mgh. I can break that down. Ek is 1/2 mv squared. And look at this, we have a mass on this side, mass on this side. Those cancel out. So the mass of the cup doesn't matter, but we already talked about that at the beginning of the year when we said that we dropped the two balls at different masses. Well, they have the same acceleration, but their velocities are going to be the same when they hit the ground. So if we want to find my speed, I just have to rearrange this formula. So I move my 2 up top, and I square root it, and I get square root 2 times 9.81 meters per second squared times my height of 1 meter, like that. And if I type that all in, 2 times 9.81 times 1, and square root my answer, I get my coffee cup is moving at 4.4 meters per second just before it hits the ground. Okay, so not too bad. So calculate the speed of the coffee cup at its midpoint. Okay. So the midpoint seems like it's a little bit trickier, but I can show you a trick. So here, we said that the coffee cup has both potential and kinetic. So with the first part of the question, we said our reference point was the bottom here, right? Because our reference point, if you're above the reference point, then you have potential energy. If you're at the reference point, you don't. So this was our reference point because we said it didn't have any potential. So if we did our law of conservation of energy, for this one, we'd say, okay, it has potential at the top. That's our before. Then after, it has potential and kinetic. And this will make it a lot harder to rearrange. But a little trick you can do is you can change your reference point. So if I move my reference point up there, what that does is that Well, now I'm at my reference point here, so I don't have any potential. And we always want to measure our potential energy from our reference point. So we're now 0.5 meters from our reference point, and it makes the question a lot easier to do. Because it's just going to be the same thing. It's going to be mgh equals 1/2 mv squared. Our masses cancel out. We move the 2 up top. We square root it, and we get this just like we did before. But now, when we do it, it's going to be 2 times 9.81 meters per second squared. But our height is going to be our height above our reference point. Before it was 1 meter above our reference point. Now it's only 1/2 meter above our reference point. So when I plug that in, I get a little bit slower, which makes sense. Okay, so you can move that reference point in these questions to help you out with how to do these. I'm just going to skip that because it's kind of the same thing. Okay, so here's a classic law of conservation of energy question. It's a roller coaster question. So initially, a 2,000 kilogram roller coaster is moving at 3 meters per second at A. It starts rolling down the track. Okay. Describe the system. So I'm just going to describe this. I'm going to box this. This is my system in here. These are my surroundings out here. So I'm going to treat this as an isolated system where this energy is just being converted from one form to another. That's what I'm going to do for this question. Okay. So assuming a frictionless surface, what is the speed of the roller coaster at B, and find the spring constant of the spring at E if the spring compresses 45 centimeters, bringing the coaster to the stop. Okay, so there's a couple parts to this question. Just give me a second. I'm going to draw out the roller coaster picture so I can write it on my board here. So just give me a second. I'm just drawing. So this is A, B, C, D. This is 10 meters. This is 5 meters. This is 2 meters. And this is 7 meters above the ground. This is 3 meters. This is E. Okay. Good. Okay, sorry, I just had to draw that. I know that's kind of weird for you. There we go. So I drew it here. So we start off with our roller coaster at here. And it says in the question that the roller coaster is moving. So it has kinetic energy. Now we're just going to start with our reference point at the bottom for now. And it's above our reference point. So at A we have potential and we have kinetic energy. So the first part of this question is asking, what is the speed of the roller coaster at B? Well, the roller coaster is still going to be moving here, because if you've ever gone on a roller coaster, the more you go down, the faster you go. So at B, it's going to have kinetic, and we're above our reference point, so it's going to have potential. So right now we have 4 energies, and that's a lot of energies to rearrange. So what we're going to do is we're going to move our reference point to our lowest point here. And what that does is it gets rid of the potential energy at B, because when the roller coaster is at B, it's at its reference point. So we have to be careful, right? We want to measure our distance above our reference point. So if this is 5 meters, this is 10 meters, then at A, it's 5 meters above our reference point. Okay, so now we're ready to solve the question. We're going to use physics principle number 5. We're going to use our energy before equals our energy after. And before we have kinetic and potential. And then after we have kinetic. Okay. We are trying to find out the speed at B. So we want to find this. And we also want to use a little tick for our kinetic energy at B, because there's kinetic here and kinetic here. And that tick just means at B. So we can break these formulas down. So we have 1/2 mv squared plus mgh equals 1/2 mv squared after. And I just put the little tick right after that v, because that's the only thing that's changing after. And if we have mass in every single one, we can cancel that out, but it has to be in every single one. If it's just missing in one of them, then we can't cancel it out. So that makes things a little bit easier. So we're trying to find this here. So these guys are being added together. So I'm going to put brackets around it. And when I move my 2 up top, I have to multiply it by that whole thing, right? And then my last step is to square root both sides. And that's how I find it. So typing this into the calculator, or actually let me write it down, and then I'll type it into the calculator. So we have 1/2. So the speed of the roller coaster at A was 3 meters per second. Squared plus 9.81 meters per second squared times my height above the reference point, which is only 5 meters, right? I'm 5 meters above my reference point. All this is A. Okay, and then I have to multiply that by 2 and square root it, and that's how I type it into my calculator. So let me type that in here. So I do my stuff in brackets first. I'd go 0.5 times 3 squared. And then I would add that to 9.81 times 5. Like that. So that's all the stuff in here. And I want to multiply that by 2 and square root it. And I have to do it in that order or else I'll get it wrong. And I get my speed at B to be 10.3 meters per second. Oops, that's off the camera. 10.3 meters per second. Okay. Good. So the second part of this question is saying, and find the spring constant of the spring at E if the spring compresses 45 centimeters, bringing the coaster to a stop. Okay. So we got to find information about E. So at E, let's move our reference point back to the ground first, because it's easier if you just have your reference point on the ground to start the question and then move it afterwards. So now it's on the ground. So at E we have spring potential energy, right? Because it took that coaster and it compressed it, and we're above the ground, which is our reference point, so it's got potential. And the roller coaster is going downwards like that. Oh, let me use a smaller one. So it starts here moving, and then it's going faster, faster, and then it slows down a little bit, and then the spring compresses it to a stop. That's what's going on here. So it doesn't have any kinetic energy here because that spring compressed it. Okay. So this is going to be our after. Our before doesn't matter. We can use A or B, but because B is a calculated answer, I'm just going to use A as my before, just because if I made a mistake with B, I don't want to use that answer because then my next one will be wrong. So I'm going to use physics principle number 5. My energy before equals my energy after. And we're going to use A and E. And let's move our reference point to here. So if we move our reference point to there, it gets rid of the potential energy there. And then A is going to be, because this is 3 meters, this is 10 meters, it's going to be 7 meters above our reference point now. So before, we have kinetic because it's moving, we have potential because it's above the reference point, and then after, all of that energy is switched into spring potential energy. Okay. So EK is 1/2 mv squared, EP is mgh, and EPS is 1/2 kx squared. Now, before we could cancel out the masses because it was in everything, but we have a mass here, but we don't have a mass here. Same thing with the 1/2. We have a 1/2 here and a 1/2 here, but because there's no 1/2 here, well, it doesn't cancel out. So that means we can't cancel out anything. So we just have to rearrange this. So I'm going to move my 2 up top. And I want to find my spring constant, so I want to move my x squared down below like that. So I'll write it out. So it's going to be 1/2. The question said that our roller coaster is 2,000 kilograms. And at A, it was moving at 3 meters per second squared. Okay. Our mass is 2,000 kilograms times 9.81. And then our height above our reference point is 7 meters. So we want to take this whole thing, multiply it by 2, and then divide it by our x squared. So it says that it compresses at 45 centimeters, so 0.45 meters. And we have to square that. Okay. So let's plug this in. It's going to do all this stuff in the brackets first. So I'm going to go 1/2 times 2,000 times 3 squared. And I'm going to add that to 2,000 times 9.81 times 7 meters above our reference point. Okay, I want to multiply that by 2, and I want to divide it by 0.45 squared, and that's our spring constant. So it's a big spring constant because it's got to stop that roller coaster. So 1, 2, 3, 4, 5, 6. So 1.4 times 10 to the 6 newtons per meter is going to be our spring constant. Okay, so I hope that helped. There's lots of homework questions like this. We just have one more to do. And there we go. So this last one is when heat is involved. It's not like any trickier with heat involved. So a 75 kilogram cyclist starts at a speed of 3 meters per second and coasts down a sidewalk to a valley 10 meters below. He starts up the other side where he coasts until he comes to a rest 3 meters above the valley. So describe the system and determine the amount of energy lost as heat. Okay, so let's draw a picture of our cyclist. So it says that the cyclist starts up top here. So this is our cyclist up here. It says that a 75 kilogram cyclist starts at a speed of 3 meters per second. So I'm going 3 meters per second and coasts down the sidewalk to a valley 10 meters below. So this valley is 10 meters below where we started. He starts up the other side where he coasts until he comes to a rest. So this is 3 meters above, and this is where my bike stops. Some terrible bike drawings there, but you get the idea. Okay, so to approach this problem, well, first thing it asks, how do we describe our system? So we could describe the system in this one as this whole picture here, right? And it's good to do the whole thing where here we have kinetic energy and we have potential energy. And as we coast down, right, we're gaining kinetic, losing potential, and then here it's stopped. So if the bottom is our reference point, it has potential energy, but we should have coasted back up to the top. So what that means in this question is that we must have some heat in this example, right? And the heat still stays within our system, the part that I boxed here. So it's still an isolated system as long as we define our system as everything in the box here. Then the heat stays in there and we can sort of keep track of it. Okay, so we're going to use the physics principle number 5. Our energy before equals our energy after. And let's move our reference point to the 3 meter mark, because that'll get rid of some potential energy here. So before we have kinetic and potential, and then after looks like we just have heat, and that's what we're trying to find. So if we move our reference point is now, or our bike is now 7 meters above our reference point, so we need to keep track of that. So it's going to be 1/2 mv squared plus mgh equals heat. Again, nothing can cancel out because there's nothing in heat. So if you have heat involved, you can never cancel anything out. So it's going to be 1/2 times our 75 kilogram cyclist, and they're moving 3 meters per second squared, times 75 times 9.81 times our 7 meter height. So you just treat heat like any other energy. It's pretty straightforward. So 0.5 times 75 times 3 squared plus 75 times 9.81 times 7. Oops. And we end up getting this much joules, and that's how much was lost as heat. So to sig digs, we just have one sig dig. We'll say it's 2 sig digs, so 5.5 times 10 to the 3 joules is our heat. Okay, so give the homework a go. There we go. Give these questions a go. There's unit review here, which would be helpful. These are all conservation of energy. These ones involve heat, so give them a go. And I'm going to post something tomorrow that you can do that involves just a little practice with the law of conservation of energy type questions. Okay. So good luck with this. Send me an email if you have any problems, and I can help you out.